Okay. The reason I nest a function here is that this parameter, it's a constant. It changes. If you change the length of the pendulum, if you change the mass, if you change the moment of inertia, you'll change this constant. In this function here, this constant is available to the nested function. It's not available outside this function here. It's a local variable. But it's defined out here in the higher order function, so it's available to the nested function. And the nested function can define the time derivative of the angle. And the first derivative is just the second the second element of the output vector, and the second derivative will solve the real pendulum equation. Okay, so headline: you do this nested function just so you can pass in a parameter. You do the nested function. And here's an ODE 23 is in this function. Here's ODE 23. There's other ODEs, by the way, ODE 45, stuff like that. And like I said, you use different solvers depending on the problem. Most problems, this works. But you might have some problems where you have to try something different. And it's a little bit of gamesmanship. You don't really know ahead of time which one. You might have to do a little trial and error to figure this out. I think every homework problem just uses this one. You don't need any more than this. Chapter 5, right. Okay, so this is a second order differential equation. It's an oscillator, but it's not a simple harmonic oscillator. It's the real pendulum, what really happens in real pendulums. Okay, going back to my, the other part of my editor here. So this is how the function is defined. This is the calling routine. Inside solve real pend is the call to ODE 23. And this is the time range. These are the initial values of the angle. And this is my constant MGL over I. So let's see how this works. I'm going to run the section. I'm just plotting 3 different numbers. By the way, you'll notice this is a small amplitude. I'm sending everything at small angles. At first, I'm doing small angles. I'm changing just the constant. So I'm doing small angles, changing the constant. You expect a frequency change. When I plot it, I multiply the amplitude by a number, just so that when I go to large angles right here, that this plot will be on the same scale. Just remember, the red and green lines are actually 1/15 smaller because of that multiplication. They're 1/15 smaller than what it shows up on the plot. That's just so I can compare the large amplitude, the blue line, to the small amplitudes, which are the red and greens. Okay, run the section. There we go. And we have red, green, and blue. Red, you will recall, is a low frequency. So the time scale, is on the horizontal axis. The red is spread out on the time scale. The green, you'll recall, is the higher frequency at low amplitudes. Red and green are both small angles, starting at small angles. Blue is starting at a large angle. You'll notice that there's a deviation. The frequency of green and blue are not the same. That a real pendulum, when you swing it at small angles, will have a different frequency than if you swing it at large angles. A real pendulum will. And this successfully solves that, shows that. It's supposed to work that way. because of the sine theta. If I just put in theta instead of sine theta, the green and blue should overlap. They should be the same frequency. And I can even do that. Let's go ahead and try that. I'm just going to get rid of the sine here. I'm just going to make it theta instead of sine of theta. And then go back, and I'm going to close the figure just to make sure it's not around when I run this. And run the section. There we go. Green and blue overlap now. As soon as I got rid of the sine. The amplitude is different. The frequencies line up. The amplitude is different, though. Okay. So, key point. When you have a parameter that you have to use in your equations, this is how to get that parameter inside. That's the key point of that. Okay. There we go. Outputs, time, and I called it X. It's actually the angle, right? Inputs, time range. This is the point 1 is the initial angle. The 0 is the initial velocity. And this is my parameter MGL over I. So I'm just changing it by a factor of 2. No, it's, there we go. See, how did I didn't think I changed this. Okay. I put the sign here, so oh, there it is. Yeah, I changed this one. This is non-zero. This is either 1 or 2. 1 or 2. 1 up here, 2 in the green and blue lines. It's 2. And then, yeah. So this is a way to get some variable parameter in to your functions. To write a solver with some sort of variable. Main thing is this variable is visible to the inner function, to the nested function. Right. Take a look. Okay. So that's that one. I just wanted to show how to pass in a variable. That's the main point of this. Second one, solving getting a root of something. There we go. I've just defined a function that is cosine x minus x. When does this equal 0? So the output is just, I just express it. There's no algebraic solution. You can't, there's no equation to invert this equation. So what you do is you create output equals whatever you're trying to make equal to 0. It's a solver. It's kind of like Excel has a solver in it. This works kind of the same way. I just define a function equals something, something, something. X equals cosine x. Right. That's what you're trying to get. When does the angle equal the cosine of the angle? When is that true? That's what we're trying to find. Yeah, that's just the name of the function. I'm going to type the function first so you can see it in the output, and then I'm going to solve it. This is just the handle to the function. This is the initial value. You've used F0 before, so this is just finding when this equals 0, and this is the value of x when this equals 0. Yes, indeed, it'll create it. There we go, and this is what it looks like. So I've typed the function, and then it finds this is when the root exists, and here it is in the workspace. Okay, so that winds up chapter 5. Moving on to chapter 6. Chapter 6 is about plotting. You guys have already done a lot. I wanted to show you just a few plotting things. The first thing is what's called subplot. And I'm going to clear my workspace and clear my figures just so we can, oh, there we go. So we can start over again. I'm also going to do format compact. And you guys, nobody told me to turn off the lights. Okay, so going back to what I'm doing, subplot. What subplot does is it lets you make window places in one figure window. You can put several plots. It's kind of a useful feature. Basically, subplot divides up a window into whatever you say. So I'm doing subplot 1, comma 2. 1 row, 2 columns. First variable is the row. Second variable are the columns. You can do 2 by 2. You can do 3 by 2. 3 rows, 2 columns. 3 by 3. Right. I'm going to show that right now. First of all, I'm going to create the subplot window using this command.
What's the last one?
That's position 1. 1, 2, it counts like this. 3, 4, and so forth. So row 1, column 1 of the subplot would be number 1. Row 1, column 2 would be number 2. Row 2, column 3 would be row 2, column 1 is number 3 and 4. It goes right to left and then down. This is only going to have one row. That's correct. Okay, so run it, and it just creates an empty plot right here. Next section, I'm just going to plot the logarithm right here. Another thing I'm going to do, I'm going to plot the log base 10. Now you could use hold on. I'm showing you another feature. You can use this also. This just draws a line on your old plot. So I'll do a double % here just to halt the execution. We'll see things one step at a time. So run this section. I'm plotting it. Go back to the figure window. Take a look. I've just plotted the logarithm. Go to the next section here. This should be the log base 10. It'll be a different line, obviously. I'm just going to add a new line to this plot. Run section. Yes. Yes. Logarithm base 10 is the blue line. Natural logarithm is the red line. Okay. Now, I'm going to put something else in the second location in the subplot. So I'm telling Matlab now, go to the next location in subplot. Instead of 1 here, I have 2. Go to the second location. We're going to add something to the second location now. Run the section. And now it just gives me a blank. I'm going to do another trick. I'm going to create a comet plot. So it works like plot, except when you do comet, well, we'll see comet right now. Comet, there's a comet. It's drawing the natural log, and you have a head of a comet and the tail of a comet. That's a way to animate your things. Right. It's an animation technique. Comet. It's a comet plot. There it is. It looks like a rocket, doesn't it? Right. There we go. There's your comet plot again. Yeah. Pretty. neat little animation. You want to impress your boss. Okay. Okay, yeah, there you go.
Your job has nothing to do with
Um,
Matlab and like, just pull it up.
Okay, so I'm going to do an easy surf, and I basically closes out the subplot. Any questions before we close, before we move on? No, it didn't, did it? Yeah, the best, it's just the way it works. The, right, so one thing you could do, let's do that.
Is run both of them
Yes,
together?
so after the comment's all done, it will draw a line, and I want to draw X, Y. I don't want to draw X, Z. Yeah, it'll do the comment, then it'll do the line. Okay. Run this section. There we go. The comment's coming up. There we go. And then then the line function drew my blue line instead of a red line. Okay. Any questions? So I'm going to get rid of the subplot now and show a 3D, which easy surf, that's a pretty good 3D thing. Okay, you guys have seen 3D before. This is nothing special. You've also seen this.
That's what I'm saying. Like, it swallowed an antelope. Antelope. A mixture between.
It looks like a snake. You're right. It does, doesn't it? Okay, here's what I want to show. Rotation. Changing your perspective. This little button right here. There are functions to do this in Matlab from the command line. Probably the easiest way to do it is just go to the figure window and click the rotate button. Now I can rotate things around. Yeah, if I view it along the x-axis,
Wait, view it directly above. Wait, view it directly above it.
there. So you see the sign here. Or do I see the sign? Oh yeah, the sign. Here's x equals 0. So it looks like negative sign.
Yeah, that's not fine.
Oh, I know what's going on. Take a look. Negative numbers to the right instead of the left.
Yeah, move it over. I think you can.
Okay.
Right.
Yeah, there. There, the negative is on the left like we like it. So that's the sign. Looking at the y. There we go. I'm going to move. There we go. The y. Keep moving the y. Same thing, same idea. Get rid of the x-axis. To rotate it in such a way that all those, there we go. This is looking pretty much right straight down the y. Yeah, it's the sign. Oh, right there, yeah. So this is looking down the diagonal. You're seeing that two-dimensional surface on edge. Anyway, so here it is directly from the top. Right. So there's ways to rotate your 3D plots. That's the point of this. I wanted to show you that. Okay. Now, next one. This particular routine is really good for aeroastro. You start initial conditions and it traces where it goes. You don't actually have to solve the equation. So what I did was I used ballistic trajectory, x and y, initial velocities in x and initial velocities in y, and just the equations of ballistic motion. The velocity in x equals the initial velocity times. I create a whole bunch of, for each mesh grid here, it's got 41 elements, you find out. So I'm just creating a vector that the velocity in x isn't changing. for all 41 elements. Velocity in y is changing. It's the acceleration due to gravity times time. I could have defined a time variable. Displacement divided by the velocity is the time, so I just did it this way. I could have done it a little differently. So velocity in y equals gt plus its original velocity. Now I streamline it. Now I'm actually not, I'm not integrating, you'll notice. So I put in the displacements, I put in the velocities, and it'll tell me the trajectory. I'm starting the initial displacements of x and y are 0, 0. You could change that, but anyway, that's how I did it. Okay, boom. Let's take a look, see what it looks like, and I hope I didn't have to.
Look, there it is, it crossed it.
Yes, it did, so I'm going to close out the figure window and just redo it. There we go. There it is. That happens sometimes. If you keep some of these algorithms, they will just keep adding to the previous figure. You don't even have to type hold on, but they do it anyway. Streamline is one of them. So you got to watch out for that a little bit. You noticed that, right? We created a 3D plot, and then Streamline just added over to it. Now, this is a neat thing about Streamline. I'm going to change my y velocity and run it again. And now I have two streamlines. Change my y velocity to 30. Run it again. Oops, I forgot to run it. There we go. Run it again. 3 streamlines. Let's go 20. Now, 20. There we go. So it's the same. It reaches, here's 20. It reaches the same height, which you expect, but it goes further. This is your 45-degree launch angle. Well, not depends. Let's see. Let's make the velocity.
It should go twice as far because it's.
Not necessarily.
It's the thing that's independent of the y.
There we go. So this is, I'm leaving y velocity the same. I'm changing x. I changed x velocity to 5. So here's 5, 10, and 20.
Yeah, so it went 35, 70,
Right. Oh, let's see. Edit. Let's see. Okay, I'm going to get rid of the top one here and the bottom one. There we go. Right. Yeah. Yeah, here's the ones where I changed the x. This changed y too. So I'm just going to, I just select it and delete it. I go to the property editor, select and delete. And then I can close the property editor now. Okay. So this is 5, x velocity is 5, x velocity is 10, x velocity is 20. Let's go 21. Oops, no. Just a little bit higher, run the section, gives me a new streamline. And I forgot which one was 21. And I'm not sure if I have, there we go. I don't remember if I can change the color. Can I change the color? Will it let me? We've been doing blue lines, so let's try a red line. Okay, just going to do it over. Oh, it accepts it. So the slightly higher velocity should, no, it doesn't change the color for me. So you might have to be just a little bit careful.
You ran it over itself, so is the blue on top of the red?
No, the red, evidently it doesn't take this command at all. Right. You can get the function handle. You can change the name colors. I'm going to do something a little bit different. I'm going to give x a really high velocity, just so we know darn well it's the. There we go. We know here's the high velocity in X. So if we get to the same height in Y, oh, I just remembered, it has to do with energy. Supposedly 45-degree angle is your maximum distance, but that's when Vx squared plus Vy squared are equal to a constant. So yeah, I increase velocity in X and I go further. Okay. I just forgot about the energy thing. Right. Right. It's just a kinematics problem. Right. Right. And I didn't hold energy constant, which is why when I increased the X velocity, it just went further. I should have held energy constant to show that 45 degrees is your maximum distance when energy is a constant. Okay, but this is mostly to illustrate streamline, how the streamline works. Okay? Okay, any questions? No questions on that. I think there's one last topic. Okay, here's another animation. I'm closing my figure, getting rid of it, and starting a new figure. This is three-dimensional plot, sine, cosine. I'm going to make Lissajous patterns. So it gives me a trace in 3 dimensions. This is just the range. You know, how far do my axes go? It's parameterized with t. Okay. And this feature, you'll get to see it as soon as I launch it. Okay. Yes, it does. So this is a Lissajous pattern.
Wait, play it again.
Play it again. Okay. Now, there's other ways to do animation. Let's see. We've seen Comet. We've seen this. There are other ways, more complicated ways to do animation. These are the easy ways to do animation. And of course, I can rotate it, look at different angles, right down on top. It looks like a roller coaster. Let's see. Run the section now. Okay. There we go. So now we have the pattern. The pattern's a little, anyway, you can change the pattern by changing this fraction. Let's go 2/3. Oops, 2/3. 2. There we go. Now I have to go to 3 pi. You'll recognize it's going from when t equals 3 pi, then the sine of 2/3 t is 2 pi. So I'm just changing my range a little bit. Got to watch out for that a little bit. I could use a variable in a function if I did this in a function. Okay. Oops. View figure toolbar. There we go. And rotate around. You can see the pattern now. It's got 3 lobes. Remember, the 3 halves had 3 lobes in the vertical. This has 3 lobes horizontally. And now I can do 5 halves. Okay. I'm going to go to 4 pi. It'll just do it twice. Okay. Run the section. There we go. Okay. So there's your animation going 2 full cycles. So basically, literally, I have talked about everything I want to say about chapter 6. We've actually finished chapter 6, the talking about it part anyway.
Did chapter 4 side layers do the thing that was on our homework assignment?
That's coming up.
Okay.
Oh, or
I didn't know if that was included in the chapter 4 homework.
I'll have to look at I'll have to look at the assignment sheet.
How cool is this right here?
It's the printed book. It should be an orange cover, except the print shop probably it's a self-printed book. Seamers, right? The Seamers book has some problems with it.